Guys, today we are going to start like a new subject, still studying things electrodynamics. That means that the charts are moving now, and you are interested in one of the most important applications in electrodynamics that actually are the what we call circuits. And today, and especially for this course, we are going to concentrate in what we call direct current circuits. That means that the source that we have for this circuit, where is the source here? Source, man, this is complicated one. Let's see for the second one. The source here is going to be is going to supply like a constant, right? If you have here the voltage of the, actually for circuits we call this, as you remember for the from high school, we call this EMF, and this value is constant in time. Okay, so you are interested actually in this class of circuits, and you are going to learn that. And man, circuits are everywhere. When you use the word circuit, that means circuit comes from, has the same roots like circulate. That means you have currents, right? Like circulating in those branches on those, those branches are actually called loops, as you can recall from high school, right? And we have, when you have circuits, and circuits, they have different goals, right? I presenting here the one that I took this in internet. This is like amplifier. This is one is amplifier for these earbuds that you're using in your cell phones, for example. And here I put another one that is I found it, I got from Wikipedia. And again, this is an amplifier, but as you can see, it doesn't matter how complicated a circuit is. In most circuits, they're composed of resistors, right, and capacitors. In this case, you have some other electronic components here, like diodes and so on. I don't but it doesn't matter. The principles that we are going to study here can apply to any kind of circuit. To just if you have like a different component in the circuit, you just have to understand how they behave, how they are affected by currents when they are powered. Okay, guys, with this being said, as we can remember, doesn't matter, that's the point I even put here. Doesn't matter how complex it looks, how complicated, what you have is actually a bunch of components that are in series or in parallel, or a combination of those. And then we already learned some techniques, right? If you go back here for our, which chapter is that, the capacitance chapter, you can remember, if you have, we already know some techniques to analyze these components, the capacitors, for example. If you there is a way to simplify your circuit and analyzing voltages and current, like going through components, if you use these techniques. We learn actually in high school two more that I'm going to talk a little bit more later. But today, let's go back, lecture 7, actually it's lecture 8. We are actually, when you have this kind of circuits, we are interested in know exactly what kind of voltage you have on this component, and what is the value of currents value, and of course the magnitude and the direction, right? Which direction the currents are flowing in every particular element in the circuit. And this can we use this for actually to understand the total load that you have in the circuit. But we have another objectives as well. We have a bunch of techniques to do that, right? So remember, the main objective is understanding, is trying to quantify these two physical quantities, the differential potential and the electric current. And we have a bunch of techniques to do that, right? Let's see here which techniques we have. Techniques. The first technique that we have to do this is actually the equivalent circuit. We can use the equivalent circuit. That means that you are going to reduce, you are going to simplify the circuit, right, to like a smaller, not so complex circuit, and then you can find the values for the current and the difference in potential. And also very this is okay, actually we did this a lot in high school. We're kind of experienced in applying this kind of equivalent circuit techniques when you talk a little bit of, before. But what you're going to learn today is something that is way more powerful, especially when your circuits are very complicated, like these circuits here, right? When you look at this kind of circuits here, it seems actually it's not so easy to simplify that. As you can see here, you have like a resistor and a capacitor in parallel. Maybe this is not so easy to simplify, and then these techniques, right, trying to reduce the circuits is not so easy in this sense, but you still can find these unknowns. You still can find the differences in potential and the electric currents if you use something that is called very powerful, that's called Kirchhoff. Yeah, wow, what is going on here? Second, guys, something wrong with mine. Let's change here. Wait a second. I have some problem with my tablet here. I don't know what's going on. One second, I'll be back, guys. Technical problems. Maybe because it's too hot. And those are called Kirchhoff Kirchhoff laws. We have actually a couple. You have this Kirchhoff laws, and you have actually two Kirchhoff laws: the first law and the second law. And I'm going to explain to you those two laws. They're quite easy, and they come from some very known physical principles that's very easy to understand. Okay, guys, so please remember this. Let's go to the next. Let's move to the next one. Before I go there, I just wanna make a brief review of how to, because we did, right, guys, for the capacitor already. So let's do like a brief review of how to reduce, how to simplify cases when you have like resistors in series and resistors in parallel. As you remember, this was something that we did in high school. This is pretty straightforward. For the first case, for example, if you are considering the case of resistors in series, all you have to do is sum up. As you remember, if you consider here point A and point B in this branch of circuit, right, the same here for the resistors in parallel. Let's consider this point A and this point B. And if this circuit here is actually, we have like a current I flowing through this circuit here. Let's put You have these currents here, I sub 1, I sub 2, and I sub n. That means n like resistors. If they're in series, of course this is the same charge is flowing through all these resistors here. That means all these currents here are the same. That means that I sub I sub is equal to I sub 2, and so forth until I sub n. And we can call this actually just I. We can lose the index here and call this just I. Okay, we know that the difference of potential between these 2 points are going to be the sum of every single difference of potential here. You can actually write analytically this as V from AB, right? The difference of potential between A and B is going to be the individual sum of all these components. V sub I1 plus V sub 2 plus V to Vn. We can use like Ohm's law here, right? Ohm's first law. We can substitute this for I1, R1 plus I sub 1, A sub 2, R2, and plus, let's put this a little bit to the left, otherwise I won't have space here to finish mine here, plus I n R n. But we know that all these currents here, they are the same, right guys? They have the same value, the same current like actually flowing through all the components, so they are all the same. Just have to substitute here. Okay, and you can rewrite this expression. Yes, actually you can actually uh, factorize this one, so it's going to give you this difference of potential here, VAV. This is equal to I, that is going to multiply R sub 1 plus R sub 2 to the nth component in this circuit, in this series circuit here, Rn. And if you divide this by I, what is going to have here is V. AB, this is going to be equal to, let's just copy here so we don't have to rewrite everything and save some time. And let's copy from here. Well, as you can see, this is what we call the equivalent resistance, right? We learned this in high school. And for the series case, you can actually put here, if I want to stick some kind of index to that, we can say series, let's say. We can actually generalize the, we can use like a summation to make this expression a little bit more compact. You can write this as being the summation from I equals 1 to n of the every single resistance in that circuit as long as they are in series. So this is a result. This is really familiar to us. We did this already in high school, but again we are going to use this, just a reminder, because we are going to compare the Kirchhoff's laws to solve like a circuit. We are going to compare to this technique of using of simplifying the circuit. Okay, we can do the same here when you have the resistors in parallel. In this case here, we have that the differential potential for every single resistance here is going to be the same. So if you are subjecting this circuit to a differential potential V sub AB, so that means that every single component here, every single resistor is going to be subjected to the exactly the same differential potential. So I'm going to write this down. So that means the differential V sub 1 equals V sub 2, and this till doesn't matter how many resistors you have here, so they're all under the same differential in potential. And you have the currents here that are also are going to use the same indexes. That means the total charge here that the source is supplying to the circuit is just the algebraic sum of every single charge. That means that the same is observed for the currents, right? So that means if you have the total current here is I, is going to be the sum of every single of the individual currents like flowing through every single component. So this is going to be I sub 1 plus I sub 2 plus to the nth element here. Okay, again we can use like Ohm's law here for every single one of these components. What you can have here is actually we have the individuals, and since they're all the same here, I'm just going to call this difference in potential just V, and then for every single one here I'm going to have V over R1 R sub 1 R sub 1 plus better copy here, I think it's easy. This sub 2 plus onto the nth element here. We can divide everything by V, so that means that let's copy here so I don't have to rewrite everything again. Can make our life easier. So divided by V, the whole expression. And again, following the example what you have before, so this is 1 over the equivalent resistance for a circuit in if you have resistors in parallel. We can actually write this down. We can generalize this using you can use like a more compact notation, use the summation. So that means that this 1 over is equivalent resistance here, but in this case I'm going to put like a P for parallel here. This is going to be, whoa, too much. The summation here on I equals 1 to n of the 1 over the inverse of each individual resistances. This is R I. Let me okay, so now we have, let me put this all in the same position here to make it prettier. So you can see all together. Okay guys, so I would like to finish this first part here. Let's just show everything. Let's see. Okay, and nothing new here. Maybe I should put some color here. Let's see. Black font. Okay, but I think you guys, nobody has any doubt here. So we did this in high school already. So I would like to move to the next topic. But just for the time being, because I'm recording for you guys, I'm going to share later. Just for this first part is done. Just in case someone wants to actually print this out, but don't worry, I'm going to share this with you later. I'm going to put in the web page. Okay,